There's 4 different assumptions related to the basic one-way ANOVA. So these 4 are normality, independence of errors, homogeneity of variance, and absence of outliers. So we'll start with normality. What I would recommend instead is to look at the skewness and kurtosis. So that will give us numbers, and that would be more objective, and we can just say, okay, is it within the criteria of the guidelines? If so, good. If not, let's find a way to deal with it. So skewness talks about, it addresses whether this curve, like if it was normal, it would look like that, whether it's skewed this way or that way. So probably you've learned that in ANOVA regression, right? And one of the more challenging part is what is negatively skewed and what is positive skewed. And so this is what they look like. So if this was scores on an exam, and if I said most people in the class tend to score pretty high, and there were few that didn't score as high, and it stretched out, would it be positively skewed or negatively skewed? Negative, yeah. So it would be negative skewed. But intuitively, it feels like positive, right? There's more people doing well. So I just often in my mind flip it. Okay, more people do well, it's negative. If more people do bad, it's positive. So that's the way I use to memorize that. And besides skewness, another aspect of the normality is kurtosis. So kurtosis looks at how pokey or how peaky, how steep, 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 and what was another term?
Oh, I was saying how drastic.
Okay, how drastic it is, yeah. So if it's a drastic high mountain, so it's positive, and if the numbers are negative, they're more flat. So if, like for example, a kurtosis of 0, that's a perfect normal curve, and it looks like this. And if it a flatter one, would be something that you would get a kurtosis of -2 or something like that. So there's different criterias, or based on different guidelines. So for Garson 2013, which is one of the textbooks, it says that normality is robust as long as the sample size is over 5 and the kurtosis is not too extreme. It's between -2 to +2. We're okay. So that's what Garson says. So robust if it meets this. So do you know what robust means, or in statistical terms? So robust means that, what does it mean in daily definition? Strong. Okay. Yeah. So it's kind of like strong. It's like it won't be impacted by violation. So it's tough. So in other words, it says that, okay, if these other conditions are met, even if normality is not met, it's okay. It's still, the ANOVA results still hold, despite normality or not normality. So that's what robust means. So it's robust against the violation of normality. Okay, so Tabachnik and Fidel, 2007, they came up with these 4 criteria. If these are all met, then it's robust. That means that we don't even need a test for normality. Even if like skewness is 100, we don't need to care. I don't think it'll likely be 100 if they're all met. So one is that the degrees of freedom within group is over 20. So degrees of freedom within group is the sample size minus the number of groups. So if, for example, we have 20 in each group and 2 groups, then we will have a degrees of freedom of 38. 20 in each group, 40 sample size total minus 2 groups. So then we would have the degree of freedom over 20. And if the sample sizes across the different groups are fairly equal, then that's another criteria. And in terms of fairly equal, what does that mean? Does 8 and 12, is that fairly equal, or does it have to be 15 and 15, exactly the same? So the definition of fairly equal based on them is the ratios within 4 to 1. So if we have a 35, 18, that's fine. So if it's 83 to 5, then that's beyond 4 to 1, and that's not fairly equal. And the third one is two-tailed, which I'll talk about the difference between two-tail and one-tail in the next slide. And then the last one is that there's no outliers. So if it meets all these four, then it's robust. We don't even need to test for skewness and kurtosis. And so the last one, the one related to one-tailed versus two-tail, this is what it's like. So usually, whether it's one-tail or two-tail, it's predetermined. It's based on the research question that we're asking. If we're testing if two means are different from each other, we don't know which one is bigger than which. We just want to see if they're the same or the different. We don't have any direction. Then we would split the 5% of the type 1 error into two and put them on both sides. So each would have 2.5% or 0.025. And then, but if we had a different type of research question, which is often the case where we're testing an intervention against a control group, our hypothesis is that the intervention group will perform better than the control group. So we're not really interested at seeing whether the control group will outperform the treatment group. We're just interested in a one-direction, one-tailed test. Then we could put all the 5% or the 0.05 p-value, alpha value, all on one side. So that's a one-tailed. So why would you do a one-tail over a two-tail?
Since you are looking for a specific direction, you want to make sure that you're maximizing the amount of assurance you have that that direction is not corrupted by error, so you put all the error at the bottom so that you're looking at giving it as much error as I'm phrasing it really wrong, but I think you know what I'm talking about.
Yeah, so we're trying to maximize the likelihood of rejecting.
There you go.
And so here, if for us to reject, we would need to get a value beyond this critical value, so beyond negative 1.96. And for here, if we load them up all here, if we get a value beyond or less than negative 1.6, then we can reject and say, okay, our hypothesis is true. So if we have a value of negative 1.7, here we reject, here we retain the null hypothesis. So that's sort of the reason, one-tail versus two-tail. Check to see if it fulfills all these four criteria. If it does, then don't bother to even run the skewness and kurtosis because it's robust. Okay, next we're going to talk about independence of error. And for the purpose of this class, we will most likely not be doing this, not be examining this. What this says is that as long as you randomize the participants, the error term should be random, independent, or normally distributed around a zero mean. So in other words, it's saying that you know something about one of the observations does not help you know something about another. And that's related to what we said in terms of the error, like that the unidentifiable factors. Those are all randomly spread out. So if we do experimental design, that's what will happen because we randomize participants. But if we don't, we're just comparing men and women. It's not an experimental design. It's not randomized. So there won't be independence of error, and there's no need to test it because we didn't randomize. So it's more based on whether you randomize the participants or not. And the third one is homogeneity of variances. So in other words, whether the variances across the different groups are the same or not. And so let's look at 4 pictures. So these are 2 overlapping curves. So of course they have equal mean and equal variance. And these two, they're shaped the same, but the position is different. So their means, which is here and here, are different, but the variance are the same. And so for this one, they have the same means, and the variance are different. So based on this graph, which variance would be larger? Blue, yeah. And then same here, blue has a larger variance and also a larger mean. So this would be like an example exam question asking whether their variance is different or not based on graphs. So what we will do to test whether the variances are the same or not, we will calculate the variance and then look at the ratio. The ratio, the term here is an F max. So just want to deconfuse you. This F max is totally unrelated to the F value that we calculated on Monday. So the F value that we calculated is calculating ANOVA, whether the mean differences are significant or not. And this F max is looking at the ratio between the largest variance against the smallest variance. So I want you to remember that. I think students in past years, they always get confused. Oh, is the F max the F or not? So these are totally different things. And if I could reinvent three-term stats, I would not use F. I would use something here. So, and so what kind of ratio is large and is too large? And what kind of ratio is acceptable would be the next question. And so here are different guidelines. So oftentimes you'll see in stats, different people say different things. So which one to believe? I think sometimes it's frustrating at the beginning, like, okay, if I'm going to memorize something for an exam or a test, which one should I memorize? Is it 3 to 1, or is it 4 to 1, or is it 10 to 1? But after more experience in the real world, I realized, okay, this is a benefit to me. Okay, if I want them to be homogeneous, and I got a ratio that was 3.5, then I would use Moore's ratio as opposed to use Box's. So I could pick the guideline that fits with mine, but I can't just say, oh, the guideline is 7 to 1. Like, I would need to make a citation. So as long as you have a legit citation, I think that's often a good way to support what you're doing related to criteria, guidelines, or the different procedures and steps that you follow in stats. So the Box 1954 came up with 3 to 1, and then Moore in 1995 said 4 to 1. But Bochnik and Fidel in the other textbook, they say, okay, we can have up to a 10 to 1 ratio as long as it meets these criteria. And so the other criteria are equal sample size, no outliers, 2 tails. Okay, so here's the homogeneity of variance test. So if equal sample size, 2-tailed, no outliers, we can use the 10 to 1 ratio. And however, not all the time we have equal sample size. So one student, Augie, he's in your cohort, right? Okay, he contacted me a few months ago and said, okay, I have this data set, I'm doing the assumptions, I do not have equal sample size, what do I do? So they don't have equal sample size, they can't use that 10 to 1 robust, 10 to 1 F max criteria. So what you can do instead is to use Welch's or Brown-Forsyth. Use these two F tests to replace the ANOVA to see if the two means are different from each other. So what the ANOVA is doing, it's testing the means across the two groups. Okay, so instead, but now we don't know, it doesn't meet the ANOVA assumptions, so we can't use ANOVA to get a reliable answer. So instead, we use these two in place of ANOVA to see if the means are different or not. So this is different from Levine's, right? Levine's test whether variances are the same, but this is testing whether the means are the same. Okay, whether the variants are the same is an assumption to go and do a next step to test the means in ANOVA. And this is directly using a different approach to test the mean differences. And there's other ways of dealing with homogeneity of variances when they're validated. One is to transform the DV scores, which we'll talk about later in another class, or to set a more stringent alpha level. So we can't trust the results, and we usually use p equals 0.05, but since the results might not be as reliable, we'll be more stringent, and we'll just adjust the p-value to p equals 0.001 and see if it meets that or not. So the last part of testing is outliers. And in terms of when we get the z-scores, what constitute of being an outlier or not? So we have two criteria. One is 3.3, and we use it if the degrees of freedom for error is 20 or larger. If it's less than 20, we use a more conservative 2.58 as the criteria. Okay, so if we have an outlier, what are some options to do? One is transform all the cases for the DV. So you transform all of them. Rather than you just pick the 3 outliers and then transform the outliers. No, you can't do that. You have to transform. Like if you're going to use a square root transformation, you're going to transform all of all of the cases in that variable. And another option is you delete the cases with outlying scores. So we found 3 outliers, we take them out, delete them. And sometimes you can also examine why are they outliers. And then, okay, they have extremely low scores, and you realize, oh, they just put 1, 1, 1, 1, 1 all the way. And so maybe they weren't really paying much attention. But if it seems like, okay, they're answering it correctly, or like they are paying attention, it seems like they're giving their honest feedback, but they're just extremely high or low. So that's another case, and you can decide whether you want to delete or not based on what you guess. And the last one, you can change the outlying scores to be less deviant. So what you would do is change an extremely large outlier to a score slightly larger than the second largest score.